All right, we're back. We're still on page 4, notes 22, Calc AB. We were talking about density functions and definite integrals and how the definite integral of a density function gives us the total mass of something. So mass of people, the mass of air, I guess, up here. And now we're going to talk about mass of oil that's in an oil slick. So an oil slick is just the oil that sits on top of a fluid, like a water or something like that. So the density of oil in a circular slick, circle, okay, circular slick, so let's draw a circle. Okay, this is our oil slick. On the surface of the ocean at a distance of r meters from the center is given by rho of r. So this tells you the density at a distance of r from the center. This is a radial density function. Radial density. Those are kind of neat. Those are like, they might be my favorite kind because like you get to do a little thinking. So when I think of these, what I think of is some, I don't know how to get the center the same. I think that might do, I think it might snap to the center when I get it. It's just that I'm not good at getting it. Okay, so we draw like a little ring, right? And then we're gonna take the ring ultimately and straighten it out. So in this case, because there's no lake in the middle that no one lives in or anything, like everything between 0 and 10,000 meters is going to be relevant. Also, this is enormous. Oh my God, 10,000 meters? That is really far. So everything from 0 out to 10,000 is relevant. So for this particular little thing, this is going to be delta R. And delta R, you know, if we care, is going to be 10,000 minus 0 divided by n. And then this part, this straight, is actually just the circumference of this. So that's going to be 2 pi and then r sub I. But what's r sub I? Well, r sub I is going to be 0 where we start plus I times delta R, which in this case is 10,000 I over n. Okay, so that's one of them. But then, you know, we should draw more. Fill this, you got to fill this whole thing up with them, right? So we want to add up all of those. Well, okay, so that's actually just the area, right? So area of a slice is going to be 2 pi r sub I delta r. So then the total mass in any one slice, the amount of oil, is going to be the area times the density. So 2 pi r sub I delta r times rho of r sub I. Okay, so then we want to add them all up. So the total is, because we're not going to take a limit yet, is approximately from 1 to n, the number of slices that we're ultimately going to make, of 2 pi r sub I. I'm going to take the delta r and put it at the end. Rho of r sub I delta r. That's our approximation. So now, to get the exact value, we'll take the limit as n approaches infinity. Limit as n approaches infinity of, I'm just going to copy and paste this guy. Duplicate of u is actually a definite integral. So where do we start and stop? Well, we start at 0 because r sub 0 would be replaces with 0. You just get 0. So 0, and then r sub n, if you replace I with n, you get n over n, those cancel, you just get 10,000. So 0 to 10,000, 10,000 of 2 pi, let's take that out, 2 pi, and then r times rho of r, but rho of r is 50 over 1 plus r, so 50r over 1 plus r dr. Find the exact value. So should we do that by hand, I guess? All right, let's take out the 50. 100 pi, 0 to 10,000. R over 1 plus r dr. Okay, so what you should do is long division. because this is an improper fraction, but what I'm going to do is plus 1 minus 1 and turn this into 100 pi, the integral from 0 to 1, 2, 3, 4. R plus 1 over 1 plus R is 1, and then minus 1 over 1 plus R dr. Look at that. That's the plus 1 minus 1 trick. It's a way of avoiding doing division, basically. Like, there's no reason to do it. You could have done division, but the key is you have to do one of the two. So this is 100 pi. Integrate 1, you get R. Integrate this thing, you get the natural log of the absolute value of 1 plus R. Whoosh. And we're going from 0 to 10,000. Okay, so this is 100 pi 10,000 minus the natural log of 10,001. And then when you plug in 0, you get, this is just 0, and this is the natural log of 1. Natural log of 1 is 0. There you go. That's your exact value. I have absolutely no idea like what that number is. Do I definitely know that it's positive? Yeah, I mean, 10,000 is definitely bigger than the natural log of 10,001, right? Because n is bigger than the natural log of n, so like that plus 1 probably doesn't really matter. So there you go. That's how much oil there is. This is in, I believe this is in kilograms. It is kilograms of oil. Kind of meaningless. Probably use a calculator on it to get some better appreciation. I don't know, maybe. Within what distance R is half of the oil slick contained? All right, so this is the entire oil slick. So I think what I can do is just say, you know, the integral from 0 to R of 50, let's use like x over 1 plus x dx. Oh, there's a 2 pi in front. No, there's 100 pi in front. What was there? 2 pi. There's only 2 pi in front. Basically, I'm taking this, changing the r's into x's so that I have a dummy variable, changing the upper bound to r. So like it's almost like an accumulation function. It is an accumulation function. Where now the amount that you have is a function of r, which is kind of a useful way to have it. This needs to be half of our previous answer. So I'm just going to cut the previous answer in half. So it needs to equal 50, 50 pi times 4 minus natural log of 1, 1, 2, 3, 1. And then we want to solve for r. I'm going to let the calculator do that. So r is approximately. All right. Let's see. So I guess it's not really checking, but I'm gonna let the calculator get a decimal for us. So rho of r is going to be 50 over 1 plus r. So we did 2 pi times the integral. There's a shortcut for integrals, by the way. I never use it because I don't think that it's faster, but I think it's shift plus, shift, and then plus. People who use the handheld tell me that that's really fast. 0 to 10,000, 50 r over, 50, just r times rho of r. I don't know why I'm typing that. dr. Okay, so this gives me 3138699.108. I don't know, sure, whatever. Let's check the exact answer. All right, so they have a negative. For some reason, they have a negative, and they flip the thing in the parentheses. We just have positive 100 pi, and then 10,000 minus natural log of 10,001. I don't know. I don't know. I literally have no idea why that's happening. But whatever. They're numerically equivalent, so we're good. So now let's see if we can solve this one last thing. Solve. I don't know. I don't know if you can do this by hand. I don't think you can. Well, I mean. Let's see what the answer is before we start saying that we don't think we can. So r is our upper bound, and then this should equal 1/2 of this, right? And then solve that for r. Oof, what's going to happen with that? I don't know, because there's r's in there, but I think that like order of operations, it'll be fine. It's not fine. Well, I mean, I don't know that this is going to solve it. Maybe. Okay, so we got some weird stuff. We have like this equation and so this is true and r is less than -1, but r is not less than -1, or r is 5003.91. So I'm gonna go with that. 5003.91, I bet, is not the exact thing. So let's do this such that r is greater than 0, and then 913. 913, probably meters. Yeah. All right, so does that make sense? Maybe. I don't know. Well, because it's like a little more than halfway to get half of it. You have to go a little more than halfway to get half of the oil that you will ever get. Does that make sense to me? I don't know. Because like, oh, well, maybe. So like what I was thinking was, like, there's more oil. It's denser the closer you are to the center. So like when you go halfway, you've filled like this. And this is like half of the oil that you'll basically get. And then this region is really big, but it just has like less oil per square meter because the density decreases. So like, yeah, I guess it does make sense that like you only have to go halfway here, right? So that gives you like a circle with half the radius versus the remaining part of the circle, which is much bigger in area, but has a lower density. So I think it makes sense. I think I've convinced myself that this makes sense. Would I have guessed it? I don't think so. But it's okay. I didn't need to guess it because we could solve it. All right, that is it for these notes. A lot of Riemann sums. Always go back and review Riemann sums. Always, it's classic. I recommend you look at that like whenever you can. You know, it's like graphing trig functions, graphing sine and cosine, moving up, down, and changing the period. You want to look at every once in a while. Riemann sums you want to look at. These are density functions. So, you know, bust these out the night before the exam. Look through them really quickly. They don't come up all the time, but when they do, why not just get the points, you know? So, all right, I'm going to call it quits on this one. I will see you in the next video, but I recorded it months ago. So I'm actually done recording the videos for Calc AB. I'm very excited about this. And for some reason, it ends on 22, even though there are 29 sets of notes for Calc AB. Whatever. All right, so I hope this was helpful, and I will see you in the next video.